our assignment that we have today is 3.3. This is the assignment that is due today. And the assignment, this one, is all the rules of differentiation. Rules for differentiation. So if any of these are things you still need to learn, I would suggest that you make a flashcard for these, because we need to put all of the things, all of the facts in this class, we need to set to memory. You cannot use a cheat sheet. There is no formula page for the AP test. You have to know everything cold. You have to know everything cold. So the rules for differentiation. Well, before we talk about the rules for differentiation, what the heck is this word differentiation? I mean, yeah, it means you can find the derivative. We're just finding the rules for finding the derivative. So one of those ways, here's rule number 1. Is the derivative of a constant. Well, what is a constant? Yeah. So if I have something like y equals 3x squared plus 4x minus 6, what is my constant? Yeah, this is my constant right here, that -6, it doesn't change. And so if I want to find a derivative of a constant, let's just look at something simple. What if I have something like y equals 3? What does that look like? It's just a horizontal line where? At 3. At positive 3. So we have something like this. What is my slope when y equals 3? 0. It's 0. I can put if I put a marble on the surface of this horizontal line, it's not going to roll. It's not going to roll, and so we say that it has a 0 slope. So the rule for the derivative of a constant, if I have something like f of x equals c, c is going to represent our constant. In fact, I'll write that c is a constant. Then my derivative is always going to be what? 0. It is going to be 0. Okay, there we go. First rule. Number 2. The power rule. Now I want to recall what all of this comes down to, this idea that Isaac Newton discovered, invented. It all comes down to this equation of the limit as h approaches 0 of our f of x plus h minus f of x over h. Everything is connected to this. Now we've noticed patterns, and so we've come up with rules based upon these patterns. So why should we memorize the power rule? Do you think that's important to have memorized the power rule?
Yes.
Yeah. This whole entire year is about the derivative. So yeah, let's go ahead and memorize this. If you do not have this memorized, then I expect that you will have this memorized even as early as this weekend. All right, so if I have, my function is a times x to the power of n, then the power rule tells me that the derivative is going to be what?
A n x to the power of n minus 1.
Of n minus 1, yep. We multiply our coefficient by the exponent, and then we subtract 1 from the exponent. So if we have, here's some examples down here where I have if f of x equals x squared, that's an ugly square, squared, or g of x equals x to the power of 7, or h of x that equals the square, the cubed root of x. Let's do a j. The j of x equals 1 over x to the power of 5. Or even how about y equals 1 over the cubed root of x squared. Now we're going to use the power rule for all of these. And we should also keep in mind that if we had multiple terms, then we just take the derivative of each one individually. I think it's really cool that it works out that way. I think it's just a lucky coincidence how nicely it comes out. So we don't have to always, I mean, imagine if this is what we were stuck with and there was no pattern. That would just be awful. I actually wonder if we didn't come up with patterns, I'm going to make the claim if we didn't have these patterns, that calculus would not be as big of an idea today, then it wouldn't be this big. It would not be as big of an idea.
Yeah, I think the problem was not the way to see things without using calculus.
Yeah. So what's the derivative of this using the power rule?
2x.
Yeah, so we have f prime, that's an ugly f. We have f prime of x equals 2x, yeah. What about the derivative of g of x?
7x.
That's it?
That's it.
To the power, yeah, don't forget the exponent.
Yeah.
We need that exponent. You guys want some think time? Do you want think time?
Yes, please.
Okay. Ian, any ideas about this one?
Um, um, 1/3 times x to the power of would it be like -2/3?
Nice. Yeah, I think it's always helpful to rewrite this using our laws of exponents to get what, Ian? X to the power of what? Yeah, 1/3, yeah. That's just our, this is not calculus. That's just our law of exponents. So if you don't know the law of exponents, this is one of our laws of exponents. We have the, let's do the 8th root of x to the power of n. And then that would give me x to the power of n eighths, I guess, n over a. That is using, that's one of our laws of exponents. That's something that you do need to know. That makes our life a lot easier to deal with. Mariah, what about the next one? What about j of x? What is j prime of x? Could I use our laws of exponents to rewrite this? Okay, so this is not using calculus yet. How can we rewrite this using our laws? This would be x to the power of what? Good, yep. Now can we use the power rule?
So it'd be -5x.
So we're subtracting one. -6, yeah. It's going to give us -6. Okay. Let's look at the next one. Maya. Maya, do you have this one? Do you know how to do it? Okay, so the first thing that I would do is use our law of exponents to rewrite this. What was our law? If I have something like the 8th root of b to the power of c, what is this law of exponents? This would be b to the power of what?
B over A.
What is it?
B over A.
Is it c? C over a? Okay. And so we're going to do the same thing with this Maya down here. And so that's going to give us what? 1 over what? X to the power of what? 2 over, it's actually a 3. Maybe it's hard to see. It might be hard to see it over there. It's supposed to be a 3. All right, so I agree with you. And so we haven't used calculus at all yet, right? These are just the laws of exponents that we've used. Now, so I have another law that says what we did, we used it up here, our negative exponent law. So I could even rewrite this as, well, what? Maya, this would be x, oops, wrong tool. Don't want that. This would give me x to the power of what? Yep. So y prime is what then?
It would be -2/3 x to the -5.
Nice. Yeah, I agree with you. Yep. That becomes our derivative function. Maya, what does the derivative function do? What's the point?
It's the
Yeah, it's this. It tells us the slope for any value of x. The derivative function tells us the slope for any value of x. And the reason I keep on bothering you guys with this, it's like, why wouldn't we know this already? Mr. All keeps on bothering us with asking, what is this derivative thing? It's because I made it several weeks into a calculus class without understanding. I'm finding the derivative, but I don't know what the derivative is. I don't want that to happen to you. So I want you to know what the bigger picture is. Why are we doing this? Why are we using, learning all these rules? It's to find that equation that gives us our slope function. All right, so what rule are we on?
3.
Yeah, so rule number 1 is how do we deal with a constant? Rule number 2 is the power rule. Rule number 3 is the constant multiple. Thomas, watch the video. Okay, rule number 3. Because I think that there are some students in this class that should be watching the video before class. I think it would really give them guidance, but I don't think Thomas should. Thomas doesn't need to be I don't.
Interrupting the entire class?
I actually don't have a problem with that, but I think that I think Thomas is already really fast thinking. And then for him to watch the videos and have that advantage on top of his other advantage, it just makes things a little bit, yeah, I don't want students to feel intimidated. All right, so we have rule number 3. This is the constant multiple rule. So if I have something like this, I have a constant and I'm multiplying by a function. So any function, I don't care what it is. So I have, I don't know, for example, y equals c times x. So we just have this constant in front. And so what do we do? In fact, What if I have, in fact, I want to rewrite this. I want to write this as this. We have y, wrong tool. I have y equals c, this is our constant of f of x. How do we take the derivative of this? You want parentheses
Yeah.
here?
Here that the f of x is 1 unit
All right,
instead of c times f.
it is c times f of x.
Yeah.
It is.
Well, no, it's sort of this way. Yeah, that also basically is making it so that the f of x is 1 unit separate from the c, but and they're not separate from each other.
Okay. How about if I write c is a constant?
That really doesn't change.
You don't feel like that helps? Okay. So what do I do? What do you do if you have a, here's an example. I have, well, let's first wrap our heads around what's going on here. Now, when we have, this is our constant multiple rule. The constant multiple rule says, I mean, if you consider the product or the power rule, what did we do with a here? This is a constant multiple rule right here. It's a times, this is a, our constant, times x to the power of n.
We multiplied it.
Yeah, or we could just move it to the side, right? Couldn't we just move it to the side? It's not really affecting anything if I just push it aside. And so our constant multiple rule says that we could rewrite this as our derivative then is just c times the derivative of f of x. Thomas, do you hate my notation?
What?
Do you hate my notation?
No, that's fine.
All right, cool.
I mean, I do remember that when you were first talking about equations, I was thinking that like, you forgot d of f over d of x.
Oh, okay. Yeah.
Yes. But it's
So
fine.
this is still the same thing, right?
Yes.
So Thomas would prefer if I wrote this as, this is probably my favorite notation. But yeah, I could rewrite this if I wanted to, just to try to change it up. So it's the same thing. We have how, Thomas, how do you read this?
I just say d of y over dx or d over d of x.
We don't say over.
Yeah.
We just say dy.
d y dx.
Huh? We just say dy dx. Yep. Do not say dy over dx. We just say dy dx. Okay. All right. So what if we have something? Let's do some examples then. This is, what is this one called? Constant multiple rule. You don't have to have the rules memorized. We have to have the rules memorized. We just don't have to have the names memorized. All right. So let's do some examples. If I have f of x equals negative 5x to the power of 5, let's do a y equals 3 over x squared. We have a g of x, which equals 4 times x t squared over 5. We have an h of x, which equals 2 times the square root of x. Tate, do you have the first one, f of x? Do you guys need more think time? Okay. Sometimes I go too fast and I really want you to have some think time. I want you to, if you can try to do these on your own, even if you make a mistake, I'm actually going to argue that if you make a mistake, then you're less likely to make that mistake again later on when it counts. Nate, do you have the first one? Nathaniel?
Yeah, it's -3/5 x.
Yeah, so we're just going to keep that constant alone. I mean, if you remember the power rule, it certainly works as well. So we're just going to keep, I'm going to do, following this rule, I'm just going to keep our constant the same. I'm going to multiply by our exponent, and then I'm going to subtract 1 from our exponent. So that's going to give us -25x to the power of 4. Is that what everybody else got? Okay. Jillian, do you have the next one?
Got -6x to the power of
Oh, nice. Okay, so did you rewrite this using our laws of exponents?
Yeah.
And so you got 3 times x to the power of -2. So when we take the derivative, I'm going to make Thomas happy. dy dx equals what?
6x.
Yeah, yep. There you go. Jack, do you have the next one? What's my constant? Wouldn't the constant be 4/5? Isn't this the same thing as 4/5 times t squared? Okay. Now I do see a problem here that nobody fixed. There's a problem with my notation here. What is it?
It's t, not x.
Yeah, it's t not x. Yeah. So in fact, in this case, t is just a constant. So there's some other value there that makes it more confusing. So in fact, if I have to take the derivative with respect to x, then this is this is what the answer is going to be. Why is it 0?
Because there's no x.
There's no x. This is all a constant. With the way I wrote this, if I take the derivative with respect to x, then my slope is 0. Do you see it? Do you see it, Jillian?
Yeah.
Okay. But I didn't mean to do that. So how do I change it so that I can make everybody happy? I can either change the t or I can change the x. I'm going to change the x. I'm going to change that to a t. So I'm going to take the derivative with respect to t. So we have our constant is 4/5 times t squared. Okay, Jack, now what?
4/5 times 2.
4/5 times 2
You get,
times what?
and then times t
Mhm.
to the power of.
Yep. And if I wanted to combine all this, what would that become? 8/5? Yeah, so that gives me 8/5 t. Yep. All right. Yeah, we need to be careful with our notation. Otherwise, I'm giving you, we're gonna keep me honest. Keep me honest. If I write something weird like that, then keep me honest. Yes, Bryn has a great way of keeping me honest. A little harsh sometimes, but she keeps me honest. All right, Thomas, do you have this one?
Yes,
Okay, did you rewrite this first?
in my head I did, yes.
Okay, in your head, how did you rewrite this?
So I rewrote it as 2 times x to the power of 1/2.
And so the derivative of this is going to be what?
2 times 1/2 times x to the power of 1/2 minus 1, which is -1/2.
And this?
That's 1.
Yep, and so that just gives me x to the power 1/2, or 1 over the square root of x.
Yes.
Yeah.
Precisely.
What's that?
Precisely.
Yeah, precisely. Okay. I wasn't sure if you said that's sweet. And it's sweet too, I guess, but precisely is probably more precise than that's sweet. Okay, so what rule are we on now?
4?
What was the first rule? Yeah, we're just taking the derivative of the constant. A derivative of a constant is always going to be what?
0.
0. Number 2, the second rule is what? The power rule. How do you feel about the power rule?
Good?
Don't you feel like this falls in the power rule as well?
Yeah.
Yeah, I feel like it does too. In fact, don't you feel like our first rule was the power rule as well? How is this the power rule?
It's
The
a
power
constant.
rule because the power of something with a, like,
This is c times x to the power what?
a 0, and anything to the power of 0 is 1.
And so this, if I take the derivative of this, so f prime of x, then using the power rule, what do?
You times everything by 0.
So I have c times 0 times x to the power of -1. But anytime I multiply by 0, it all goes to 0. So we don't have anything there. So I almost feel like we're making things more difficult than they need to be. Do we really need all these rules? I don't know. Sometimes it helps to see them listed this way so that it allows us to wrap our heads around the different forms that we might see, but it all comes down to the power rule. Continue. Number what?
4.
Number 4. Number 4 is the sum and difference rule. So rule number 4 is the sum and difference rule. So if I have something like d dx, this is my derivative of some function with multiple terms separated by addition and subtraction. Actually, that's the definition of a term, is that you have some quantity that's separated by addition and subtraction. Then I can do the derivative individually by terms. So this would be our du dx plus or minus dv dx. Maybe you don't like the notation, but let's do some examples so we understand what is expected in this rule. What is expected in this rule if I have something like y equals 5x squared minus the square root of 2 times x cubed minus the square root of x. Then when I take the derivative of this, I can find the derivative for each individual term and then just add them together at the end. Okay, so my derivative then is going to be what?
And x.
Do you want some think time? Think time? Mr. Hall, just give us the answer. I don't want to think. Just give us the answer. Well, you have to think. Math, skills, you can't just pour a skill into your head. You have to work for it. Who's ever seen Matrix? That would be cool.
Is this, so the second term, is it just the square root of 2? Or is it the square root of 2x?
What's my constant?
No, it's just the way you did square root is not clear.
Would it help? Oh, I see what you're saying. What if I go like, sometimes this is what I sort of, first of all, well, what if I do something like this? I just put a little end part here. Is that better?
Okay, that works. Now that it's clear.
Okay. In fact, generally speaking, we would always put this in front so that there's no confusion. Kyler, what'd you get? Kyler, what notation did you use? Did you use y prime or dy dx? Or d dx?
He's not here.
Kyler's not here?
No.
Oh, okay. I apologize. How about is Logan? Logan, do you have this one? Uh-huh. Yep. All right, so let's consider if I have y equals a times x to the power of n, let's consider our power rule. What is the, using our power rule, what does this function become, Logan?
Becomes a in x in minus one.
Okay, in this example here, what is a?
Two.
It's actually negative the square root of 2.
Okay.
Do you see that it's not a variable?
Yeah.
So all of that is just this a value, it's a constant. And then we have x, what's n? The n is 3. This is a, followed by an x to the power of 3. Because it's not a variable. There's no variable. I'm taking the derivative with respect to x. Because I'm taking the derivative with respect to x, then the square root of 2, that's just a constant. You can plug it in your calculator and you get something like, I don't know, 1.2358, something like that, right? It's just a number. This is just a number. Just like this is a number. This is our variable here. And since we're taking the derivative with respect to our variable, then we just treat this as a constant. So a is what? What's n? So I'm just going to write 3 times the square root of 2. I did that in front because Bryn's going to say, if I write it like this, Bryn's going to say, Mr. Hall, I don't know whether that 3 is inside of the square root or not.
Well, it's a fair point.
It is a fair point. I actually absolutely agree. And that's why normally I would write this as x cubed times the square root of 2 for that very purpose. We don't know whether, if you put this behind it, then we have that confusion. So in standard form, we really should write it like this. But
X before the square root of 2 as well.
the x before, yeah, before the square, yeah,
And then after the 3.
yes. So what is left over?
X squared.
X squared. Yeah, I would prefer to see the x squared in front as well, just so that there's no confusion. So we have an x squared here.
And so we have to be completely proper, we want to put the 3x squared and square root of 2 before the 10x. Compared to 3.
Yes.
Okay, just checking.
Yep, you are correct. And you know what? When remember that there's two parts of your AP test. Well, I could actually think of it as there's four parts, right? There's a calculator and no calculator portion. About half the test is with a calculator and half without. And then there's multiple choice versus a free response. Now with the free response, it doesn't matter. Don't worry about all of the arithmetic. What they're trying to measure is the calculus. So it doesn't matter whether, this is in front or whatever like that. That's just, really, we're just looking at trying to make it look, pretty, trying to organize it, but you don't have to do that with our free response. All right, what about this last one here? What is this if I rewrite it using our laws of exponents? Yeah, so if I take the derivative of that, what do I get? Well, it's actually negative, right? We should have that negative. So if we take the derivative of that, what is it? Yeah, and then we're done. I don't want you to don't worry about when it comes to the free response on your AP test, do not worry about trying to, the arithmetic. Don't worry about arithmetic. Just stop there.
It's clear what you're trying to say.
What's that?
As long as it's clear what you're trying to say.
Exactly. Yeah. As long as they can read what you wrote down, then you're good.
So put square root in the x. Because that is the source of potential confusion.
Yep. All right. So let's move on. Let's do another example. So I have g of x equals negative x to the power of 4 over 2 plus 3x over 5, and then minus 7 over x. I'm going to give you a little bit of think time. Should we do it this way?
No.
That would be awful. Oh, thank goodness that we don't have to do that. I'm so happy for the shortcuts. I am so happy that we have a shortcut. So let's not do it this way. Mr. Morgan, do you have the first term? Negative 4x cubed divided by 2, yeah. Yeah, your 1/2 is just a constant. If you prefer to rewrite this as what, negative 1/2 times 3. Oh, what happened to the 3? The 3. No, I'm sorry, it's 4. I'm sorry. Sorry. 4 times x to the power of 3, right? And that's the same thing as this. I don't care which way you write it. Mariah, do you have the next one? Yeah, that's just our constant. So we're going to multiply by our exponent, which is 1, times x to the power of 0, which just becomes 1. So I have 3/5 times 3/5 times 1 times 1, which is just 3/5, yeah. If you're using the power rule. Or you can use our constant multiple rule. And the constant multiple rule just says here's our constant.
But it's not actually, oh, I guess, yeah. Never mind. Got my name confused with that one.
Bryn, do you have the last one?
Would that be, negative, wait, never mind. Positive, or plus, 7 over x squared?
Over x squared like this?
7 over x squared.
7 over x
7
squared.
divided by x.
I listened to you wrong. 7 over x squared, like this?
Yeah.
Okay, good. Now some of you are able to do this in your heads. Now I notice with myself, when I try to fit too much in my head, I end up making mistakes. I noticed that with my son as well. He thinks he has it all figured out and he's very confident. And then he starts to do things and skipping steps and getting the wrong answer. So I would recommend, until you feel a lot more confident with this, that we write this out using our laws of exponents. How can I rewrite this so I can use the power rule?
There's 7x power of -1.
Yep. And now with our power rule, our a is -7, our n is -1. So that gives us -7 times -1 times x to the power. We subtract 1 from our exponent. That gives us -2. Okay, and then what Bryn did, did you do this in your head or did you?
Yeah, I did that in my head.
Okay.
So basically, I popped the x down to the denominator because everything else is already a fraction, it just fit in.
Yep.
And then I made it, and then it's because there's 2 negatives that cancel out, it's positive that way.
Good. I would still advise everybody, including Bryn, to write it out this way. Because that's where we make
I
mistakes.
do write it out, I then just erase it once I figure it out.
Oh, I see. This is, but this,
That's why I use white cord marker all the time, because I don't like having a ton of work making everything look weird,
that makes sense. Yep,
but I do write out the work while I'm using it.
good. That's what I want to hear. This is where we make most of the mistakes when we try to skip a step. So even though it might seem tedious to write something down, write it down anyway. It's better to deal with the tedium than to get the wrong answer. Moving on. All right, so here is, so that's it. Oh, no, there's 5. There are 5, no 6. Oh, huh, okay. I need to step it up. Not going fast enough. What's that? I'm sorry, what?
If we only have 2 rules left because we're on rule number 4, just finish rule number 4, then we have 25 minutes for the next 2.
There's some other stuff I wanted to cover. I want to know, does y equals x to the power of 4 minus 2x squared plus 2 have any horizontal tangents?
You mean vertical? You mean vertical tangent?
I mean horizontal tangents. How do you find them?
I'm thinking graphically, it has a kind of part where it swaps from positive slope to negative slope.
What shape should this function give us? Shouldn't it be like a W? Should look something like, I don't like that. Now, of course, it could be something like this. I don't know, but generally speaking, it's going to be this W shape. This is what a quartic does. Now, it's possible for a quartic to be smooth on the bottom like this, but it's not going to be a parabola. It's going to be what's that?
Very, very steep.
Yeah, it's going to be a lot steeper than a parabola. And it's going to be more flat down here at the bottom as well than a parabola.
But it's still gonna have a 0. So
Yeah, so it does make sense that we should still have a 0 slope in there somewhere. How do you find a 0 slope? Thomas?
When all the x's get canceled out, there should be a slope, there should be a slope of 0 at the tangent.
If all the x's get canceled out,
Like if there's only a constant left, because the slope would be 0, so the derivative would be 0, wouldn't it? Well, that works too.
find the derivative. And set it equal to 0. Then solve for x. Okay. Think time. Jack, does that make sense? Jack, so what is my derivative?
Be 4x. cubed, and then minus 4x.
So what's the derivative of a constant? What's,
Or no, it's 0.
it's just 0. Yeah, it's just 0. The derivative of a constant is 0. So we just leave it alone. Okay, so what was the next step after we find the derivative? Yeah, set it equal to 0 and solve for x. So this gives us 0. Why am I putting a 0 here?
But you're setting it equal to 0.
Why? What's the relevance?
You want to find a horizontal slope, and that's when the slope is 0.
Yeah, I want to find a horizontal slope, and a horizontal slope is a slope of 0. So let's put in 0 there. And now I need to solve for x. Gonna give some think time. How many slopes are you finding?
How do you mean, how many points?
How many horizontal slopes are we finding? Or horizontal, sorry. How many horizontal tangents are we finding?
I found 3 so far.
There are 3. I agree with you. So how do we find them? What do I do at this point? How do I solve for x? We need to factor. What if I divide both sides by 4x? Is that okay? Yeah, you're going to lose values. Do not do that. You're going to lose values by doing that. That would be equivalent to if I have 0 equals x squared plus 8x plus 15. I factor this to get x plus 5 times x plus 3. I now divide both sides by x plus 5. I'm losing a value by doing that. Do not divide out values when you're trying to solve for x. You're going to miss some important values. All right. So what do I do instead? I need to factor. How do I factor this?
You could first factor out an x.
I can factor out an x and a 4. Yeah, I can factor out an x and a 4. So that's going to give me 4x times what?
X squared minus one.
Okay. Which looks suspiciously like
Difference of squares.
a difference of squares. So that's going to give us 4x times,
X plus one.
so what are my x values that give me 0 over here?
One.
0, 1, negative.
There you go. Should we graph it and find out?
Yeah.
Let's see how we did. Those are our horizontal tangents. Bentley, do you see the difference of squares here?
Yeah.
Cool. Yeah, because I have x squared minus 1, and minus 1 is the same thing as minus 1 squared, so I have a difference of squares. That's one of our special factors. All right, let's go ahead and graph this and see if we do indeed have 0 slopes at 0, 1, and negative 1. Yeah, y equals x to the power of 4 minus 2x squared plus 2. And we said we have 0 slopes at negative 1, 0, and 1. How did we do?
Pretty good.
Yeah, those are our 0 slopes. Thomas, would your method have worked? Yeah, I don't think your method would have worked.
Definitely not.
I think it's really interesting, though. I mean, that we should, to be inquisitive like that is what helps cement the knowledge. So there's nothing, I think that having some ideas like that and challenging your teacher is actually a really helpful thing. So let's go ahead and move on. Rule number 5. Rule number 5 is called the product rule. What does product mean?
Multiply.
So if, this is called the product rule. If I have y equals f of x times g of x. So we have two functions inside of so I have two functions. My function is made up of two functions, a linear and a linear, or a linear and a quadratic, or a linear and exponential, or whatever else. So the way that the product rule is done as follows. The derivative is going to be f of x times f prime of x. Sorry, f of x times g prime of x. So I take the derivative. So we take the first function times the derivative of the second function plus the second function times the derivative of the first function. How did we come up with this crazy rule?
Looking at examples.
Yeah, we saw patterns. I'm curious to know, Thomas, you said that Isaac Newton knew the power rule.
Yes.
Did he know the product rule? I wonder about that.
Both of that.
Okay. How many of these rules that we're learning did Isaac Newton know? All right, let's do an example. Here is my example. I have y equals x squared plus 3x plus 5 times 2x to the power of 5 plus 7x minus 11. Now, without the product rule, we could distribute, and distribute, then we'd have a bunch of we'd combine our like terms, and then you could just take the derivative of each individually. Or we can use the product rule. So I don't want to do that. I don't want to distribute all this. So I'm going to do the product rule instead. What does the product rule say to do?
Derivative of each part separately and then multiply the regular part times the derivative on both sides and then add it.
So let's do the first one. We have f of x, which is, that's what this piece here is. I'm not going to do anything with that. So I have y prime equals x squared plus 3x plus 5. Now I'm going to take the derivative of the second function. What's the derivative of the second function? What's the derivative of that?
X to the fourth,
10x to the power fourth
7.
plus 7. That's it? Okay, minus 0, yep. And then plus our second function, which is 2x to the power of 5 plus 7x minus 11 times what?
3.
2x plus 3. Yep. Can I stop there with free response on the AP test? Can I stop there?
Yeah.
Yes, you should stop there. Don't get caught up in all of the arithmetic. That's just going to be messy and ugly and you'll end up making a mistake. Just stop there. Another one. Here's my next example. G of x equals x squared plus 1 times 5 minus 2 over the square root of x. I'm going to give you a little bit of think time. What's this rule called? The product rule. We still have to do the quotient rule, so we're going to go ahead and do this one now. All right, so my derivative is what? What do I do first?
First you get x squared plus 1.
X squared plus 1.
Parentheses times, pretty sure this is correct, -2 to -2 over, I want to say.
I'm not going to skip a step. I don't want to skip a step. Let's rewrite this using our laws of exponents. What do we get?
-2x to the -1/2.
Yeah,
So that just be square root of x.
so that's going to give us, we're going to take this exponent, multiply it to the -2, which gives us what?
That's
1. And so that leaves us with x to the power of, I'm actually not going to skip this. I'm skipping steps. Okay. So I have this -2 using our power rule times -1/2 times x to the power of, -3/2. Okay. Are we done? We don't need to simplify, not with free response. Are we done then? What about this?
Oh,
Don't we have to, what about this part? We skipped an entire part. Plus,
5 minus 2 over the square root of x.
okay. times 2x, yeah. Now we're done. That is so cool that we have this pattern. This would be so messy. When I get this one, it wouldn't be too bad, right? I'd distribute here and here and then here and here, and then we have a bunch of terms, and then we take the derivative of each. That one wouldn't be so bad. But they could get really ugly. All right, so we're going to move on to our last rule, rule number 6. This is our quotient rule. You guys still copying? Tate, you good? Go. Winnie, you good? Okay, the last one, number 6. Rule number 6 is called the quotient rule. If I have a function y equals f of x divided by g of x implied by the quotient rule, then when I take the derivative of this, the derivative of this is going to be g, I'm going to take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. That looks really ugly, but there is a way, there's a shortcut to memorize this. Sort of snappy, I think. It's low to high minus high to low over low low. Low to high minus high to low over low low. This is how we're going to remember it. Low d high minus high d low over low low. Low to high minus high to low over low low. What does this d mean? The derivative. So as we're taking the low, we're taking the denominator low d, the derivative of the high, minus high, the function in the numerator, d low times the derivative of the denominator over low low. Is this a derivative down here in the denominator? No, we're just taking the denominator times the denominator. Sort of cool that this even works. Low to high minus high to low over low low. Everybody together. Low to high minus high to low over low low. One more time. Low to high minus high to low over low low. I feel like I lost you. One more time. Low to high minus high to low over low low. That's how we're going to memorize this. Low to high minus high to low over low low. Okay, here is an example. Are you guys still copying? We're good? Mariah, you caught up? Maya, you good? Okay, here's our example. I know we don't have a lot of time left. Here's our example. I have f of x equals x squared minus 1 over x squared plus 1. Low to high minus high to low over low low. Ian, you good? Are you done? Mr. Hall, I just have 4 more minutes. I just want to wait it out. Ian, where do I start? What's low D high? What's low?
X squared plus 1.
Low. D high. What is D high? And what's the derivative of a constant?
Zero.
Yep. So low D high minus what? What's high? X squared minus 1. D low. which is
2x.
2x over low.
That
X,
would be.
x quad plus 2x squared. Or of course, we do that squared.
Or all squared, yeah. Should I simplify all this?
You could, but
No, don't. If it's a free response, stop.
Why?
Because you're going to, my concern is,
There's gonna take you a good minute at the least in each question.
yeah, you're losing time for your other problems. So yeah, don't do that. There's one other thing. I know I only have 2 more minutes
Trying to
left.
go back, sure, go ahead and do
We're
it.
probably just gonna do it wrong, so
Here,
I would do
You-
it wrong.
there's one last thing I want to talk about. I know I only have 2 minutes left. You can take a second derivative or a third derivative or the fourth derivative. In fact, if you have an equation for acceleration, if you take the derivative of acceleration, you get velocity. Sorry, let's try that over again. I'm thinking of the wrong way. If I have an equation for distance over time, the derivative of that is the velocity. The derivative of that is the acceleration. So we can take multiple derivatives.
Derivative over the derivative of the derivative of the derivative.
The derivative of the derivative of the derivative, I think it's it's velocity, acceleration. I think they call it a jolt as the third derivative, like what you would experience on at a carnival.
Hey, did we say we'd be going over these books, right?
So if I have f prime of x, that is my dy dx. That's my first derivative. If I have f double prime of x, that's my second derivative. And the way that they write it is this way. This is the second derivative. And then anything more, you're going to write it like this. You're going to just write with a little, parentheses 3. This would be the third derivative. We'd have d to the power. So d, what would that be? D, I would just say the third derivative. I'm actually not sure how to read this. And that would be our third derivative. Okay, that's it. All right, I have 1:15. Have a wonderful day. Have a wonderful weekend, and I'll see you on Tuesday.
Mr. Hall?
Yes, sir.
I'm going to be here on Tuesday.
You're not going to be here on Tuesday. If you're not here on Tuesday, I do expect that you are going to watch the video, either